Let's practice another example on these partial fractions. Here we have to show that the series is convergent. So what we do is we check the sequence of partial sums and see whether that sequence has a limit, right? So the partial sums mean the sum of the first n terms. Now if I write if I denote the partial sum with Sn, we have this one, right? So that means we can even write this sum of finite terms also as in a series notation. For simplicity we can write it in a series notation, but then you have to mention both starting point and the end point. Okay, now normally what we do is we write the series like this and we mention the starting point, and here see the end point is n because of the n term in this partial fraction, right? So if I write the n here, see the series also runs through the n variable and the end point is n, and that is a bit confusing. So what we can do is we can denote the general term in our series with I, right? And then we can start at 1 and end the series at n. Okay, so don't give too much significance for these variable names, right? They are just dummy variables. You can use whatever the name you prefer, right? But the reason for not using n here is because, like, within this equation itself, the n represents the last variable, right? Last term. So here at the final point you should mention n. So if we use the kind of this general variable, like if we use n for the general term also, these two will get mixed up, right? But here the general term is represented by n and we start n at 1 and goes up to infinity. Okay, so but here it was a different case because we are dealing with partial sums, which is the sum of a certain number of finite terms. So we start at the first point and we end the sum at this n number. Say for example, if we have x10, that means we do the summation of I times I plus 1 from starting from I equals 1 to 10, right? So the last point here will be 10 plus 1. Okay, and here we will start at this point and goes up to the 10th position, right? Okay, so what we have to do is we have to compute the partial sum sequence and see whether you have a limit for the partial sum sequence. We need to check whether this one have a limit. Okay, so for that you can see, now if this is the very first time that you are doing these sort of problems, you might not like this method will not be trivial, right? But once you have some sort of experience, these are kind of standard simplification methods. Okay, so you can see that this general term can be written like this. Now this Sn term, no, not the Sn term, the general term inside the sigma notation of Sn term, which is I times I plus 1, can be written like this. Okay, I plus 1. Now this is actually the partial fractions, right? Not the partial sum, this is partial fraction. Like we have used the techniques of partial fraction to decompose this left hand side. Okay, right, so simply we can write this one in the form of two separate fractions, right? The reason for doing it is because now Sn means the sum of this term starting from y equals 1 to n, right? That means the sum of this one starting from y equals to goes up to n. So, and if we expand this series, that means this is the general term inside the series. So we should start from I equals 1, and I equals 1 means we should substitute I equals 1 for both cases, right? So this is the I equals 1, and since this is a series, we should have a plus sign in between the terms, and this is the I equals 2, that is half minus 1 over 3. Okay, and I equals 3 will be 1 over 3 minus 1 over 4. Okay, and likewise it will go up to, let's take I equals n minus 1, then that will be 1 over n minus 1 plus 1 over n, and this is not plus, it will be minus. And the last term, now since we have a finite term, we can specifically consider about the last term, but if it was infinity, we cannot really consider the last term, right? But here, since it is finite, we have a specific last term, right? Now see, there is a nice cancellation in these terms with this plus and minus stuffs. All these terms will get cancelled out with this, will be cancelling out with the term before this one. This one will get cancelled out with this one, right? So you can see, but the thing is, there are no terms remaining to cancel out this one as well as for this one. So what happens is, the partial sum Sn, which was equal to this one, will be reduced down to 1 minus 1 over n plus 1, right? Because these two will be the only terms that remains. Okay, so we started with this series, like we were going to prove that this given series is convergent. So according to the definition of convergence, we need the partial sum sequence, and for the partial sum sequence, we saw that the partial sum can be written like this, and then this general term of the series in the partial sum can be decomposed like this. So if we expand and write these like if we did not do this decomposition, we won't be able to figure out this cancellation, right? So that's the main reason for having this sort of a decomposition, because once you decompose, luckily we had a negative sign in between. Okay, so once the decomposition is done, and when we expand the series notation, we saw a nice cancellation. This will be cancelled out with this one, this will be cancelled out with this one, and likewise most of the terms will get cancelled out, and the very first term and the very last term will remain, right? So the partial sum sequence will be like this. The nth term of the partial sum sequence will be like this. So at the end, what we have is a sequence like this, right? N plus 1. So our partial sum sequence will be like this. Now if you need to find terms, you can directly substitute the values like to this simplified expression and evaluate the required terms, but you really don't need like you don't have to do this one. What you need is the general term of the partial sum sequence, right? So once you have this expression, you can easily compute the limit of our partial sum sequence, right? Which is 1 minus 1 over n plus 1, and that is equal to 1. When n takes a larger value, this becomes 0. So what remains is 1, right? But see, if you did not do this simplification or this decomposition, then the partial sum is represented like this. Okay, I goes from 1 to n. Now here we it's very difficult to think about a limit of, if we only consider this notation, then the limit will be something like this. Okay, we won't be able to simplify it any further if we remain the partial sum in this notation. That is the reason for doing this sort of a computation at the beginning, and then we simplified, it's like we get rid of this sigma notation in the nth term of the partial sum. So once we do that, we can directly compute the limit of the partial sum. Okay, then we can see that there is a limit for the partial sum. Therefore the series converges, and we can write down the value of the series as equal to 1. Okay, right. Well, now this series is not the partial sum. Okay, this is the complete infinite series, and the addition of all these terms will be equal to 1 from the definition, right? Because the sequence converges, and if the sequence converges, we say that the series converges, and also this is defined like that, right? The sum of the series is, if the series converges, then we define the series to be equal to the limit of this partial sum, which is 1 in this case.